Thanks everyone for joining today. I'm going to do a quick intro and introduce you to the speakers for today. So let me share my screen here. Welcome to the Research and Tech Call. Today we're going to be hearing from Hussein, Sonia, and Dermot about some technology that they have that helps them create a visibility index for roadside billboards worldwide. So before we start that, I just wanted to remind everyone on the call today that our summit is coming up soon. So if you want to, take a quick scan of this QR code and it'll bring you right to the website so you can learn more about some of the really cool speakers that we've already announced. More coming soon, but so far we have some really heavy hitters from CVS, Microsoft, BBC, Claire's, and Canvas Worldwide. So there's that QR code again, if you missed it the first go around. And really that's the only housekeeping I had for today. So without any further ado, I will push it over to Hussein, who can introduce you to his speakers for today.
Thank you, Blake. Thank you very much. Thank you, DPA. Thank you, Ajay, for all the support you are showing. Let me share my screen. Can you see my screen?
Yep, looks good.
All right. Thank you very much, gentlemen. Thank you, ladies, for attending this webinar. Today, we're going to be talking about using advanced machine learning process to extract visibility index for billboards, roadside billboards, regardless digital, static, or any type of billboards. And our agenda will be telling our story, the machine learning model, and then we're going to be moving to question and answer. It's true, this is what you see. It's Vegas. This is where it happened. It all happened in Vegas in CES 2019. And this time what happened in Vegas, hopefully we're going to be sharing with you. I've met Professor Sonia Coleman, Professor of Vision System at Ulster University, and Dr. Dermot Kerr, Senior Lecturer at Ulster University, where they have created a computational model of the salamander retinal ganglion cells using an advanced machine learning processes. And of course, Professor Coleman is part of Ulster School of Computing and Intelligent System. She's also a cognitive robotic team leader with the Intelligent System Research Center. Dr. Kerr, he's a senior lecturer. Also, he has a vast work in the visual neuroscience business. What makes Ulster University special? They have a long and successful heritage of creating value from research knowledge, and this is why we selected them. Why salamander? Salamander is a very nice creature to us, and hence the name of the previous project, we called it salamander. Salamander, what makes it different than any other creature is they have a robust nerve system that can record any experiments on them. And most importantly, they have a huge, their photoreceptors has an outer segment diameter of 10 to 12, 10 to 13 microns versus a human outer segment of 2 microns. What is a salamander VI? Salamander VI uses an array of artificial intelligence measurement to define the physical attribute of any given billboard. It's the first machine learning process, so there's no human interface, there's no human interaction, very minimal. And most importantly, it ascribes a precise value for any given billboard roadside globally. What is our current industry standards, our current industry measures or visibility index? We use it's a very highly dependent on a human. We use a human to come up with the value. And most importantly, different governing bodies in different countries, they use different methodologies and different standards. And unfortunately, it's not available in most of the third world countries or less developed countries. So what do we study? We study the physical attributes of the billboard. So the height, the size, the format, the angle to the road, the distance from the roadside, any obstacle of viewing, the contact zone, all these area of physical attributes, they are put into the machine learning process where we can come up with a visibility index for each and every single billboard. Who will benefit out of this? Governing bodies surely, and we are hoping to cooperate with Geopath, Root in the UK. We would like to contribute to their current success and give them some support, a scalable solution that can help them remove the human dependency. Of course, buyers and sellers will also benefit out of this because it will give you an accurate visibility measurement. It's a data enriched, it's a new dimension of a data enriched buying decision. And of course, this will lead to a higher return on investment for buyers. The unified index itself being unified and among all billboards will help optimize revenue for sellers. And most importantly, it's a very scalable solution. I will leave the floor now to Dr. Kerr, who will take the floor and explain a little bit about the machine learning. Doctor?
Thank you, Hussein. Can everyone hear me okay?
Sounds good.
Perfect. Great, thanks, Hussein. Can we move to the next slide, please? So as Hussein mentioned, myself and Professor Sonia were really interested in computer vision, but in particular around what we call biologically inspired computer vision. And we're really interested in learning how not just animals or humans, but all biological creatures and how they process visual information, and then how we can be inspired by those techniques and apply them for real-world computer vision problems. So that's what we're going to present today, is really how we took inspiration around how humans process visual information and apply that to this particular research area, which is around computing visibility of billboards. So in this image sequence here, we can see that every billboard that passes by the screen has unique visibility characteristics. These characteristics are determined by the billboard and also the environment within the billboard is contained. We can see the billboards as they pass at the side of the road, as the vehicle moves along. Some of the billboards are obscured by other structures in the environment, such as telegraph poles, other vehicles, other signs. Other environmental conditions can also affect the visibility of a billboard. For example, the lighting that's available, the current weather conditions, any buildings that are in the environment, or even the speed of the vehicle as it moves along. Previously, when people considered the visibility of billboards, they often based this visibility on static measurements, such as distance, the size of the billboard, the distance from the road. And we sort of felt that these measures, while were a good start in terms of measuring visibility, they're not always reflective of what we consider real world viewing conditions, what people actually see as they move along the road in terms of the content within the billboard. So we wanted to develop a data-driven algorithmic approach to billboard visibility and remove any subjective measures from the measures that are computed. So can we move to the next slide, please? So what we've actually developed is a completely automated AI-based solution that can measure visibility based on actual real-world viewing conditions. And in this presentation, what we're going to show is an example study area where we computed visibility of a selected number of billboards. The study area here is based in Arlington, Texas. It's just a random area. It's not a unique area for any means. It was just the chosen study area that we selected. In the area, what we have here is 5 billboards where the visibility was computed automatically using our approach. So there's 5 push pins that are visible here, the red push pins. And in the center of the push pin, there's a numerical value, and this corresponds to the visibility metric that was automatically computed. So if we move to the next slide. So zooming in a little bit closer, we can see, particularly in this area, there's quite a big difference between 2 billboards. So the one on the left has a visibility that's been computed as the value 17, and the one on the right has a visibility of 401. So what creates this distance or this difference in billboard visibility? So, well, in our approach, what we do is we construct this metric based on the visual perception of the billboard based on imagery that's collected around that billboard. So if we can move to the next slide, please. So looking at our 401 example, what we can see here is the billboard location indicated by the pushpin. And around that, we can see a number of black dots. These black dots are the locations where we have imagery of the billboard. At each of these black dots, what we actually have is an image that points towards the billboard, so we can see the billboard from that image, and that contains lots of really useful information. For us, it's a visual image, so we can see the real world conditions, and we can extract information like the size of the billboard from each position. So the first thing we do in our approach is we calculate the distance from each viewing location to the billboard, and we also compute other important metrics such as the heading and the angle of the billboard with respect to the viewpoint location. Next slide, please. Then what we do is we extract all the images from this location, and we use deep learning technology. So this is a completely automated deep learning network, and we pass in the images and the billboard is automatically extracted from the scene. Using this information around the billboard, we are able to estimate the billboard size, and we combine that alongside the other measures such as the distance, the angle. We also incorporate some measures around visual acuity of the human visual system, which corresponds to how far humans can perceive visual information. And we bring all this data together in order to construct a visibility metric. Now, it's really, really important to note that it doesn't matter if we have 5 images around a billboard or 500 images around a billboard. The technique in itself isn't reliant on a specific number of images. It's solely based on the data that's extracted from each of the images together. So if we look a little bit closer here now at these 2 examples, if we consider the billboard on the left, the one with the visibility of 17, we can see that the billboard area in each of the images is really, really small. And this corresponds to the distance of the billboard from the viewpoint in the road. If we look at the billboard on the right, we can see that one has the visibility of 401, and the billboard in the images is much larger, and we can see it from a number of locations around the billboard. So there's a number of roads where you can extract that information. So we can see now how this metric starts to come together. So next slide, please. So just another still example of these 2 billboards where we can see from a single image the difference between them. The one on the left with the lower number is really far from the road, really small. The one on the right, it's much larger, and there are lots more roads around there where you can view the billboard. Next slide, please.
So what exactly is needed to use this type of visibility metric? So we need accurate positional information of the billboard. We also need imagery surrounding and containing the billboard. This can be obtained from pre-existing large data sets such as Google Street View or Mapillary, or your own sources such as dashcam footage. Along with the imagery, you also need the positional information where the image was captured. The salamander system then does its magic automatically with no human input needed. It makes use of state-of-the-art deep learning networks to analyze the scene and extract the billboards. Using a human visual system-based model, it then calculates the billboard visibility. The salamander system is driven by the data in and around the billboard location and ensures that all billboard visibilities are calculated in the same way, and this ensures global consistency. The system is fully transparent in that you can see how each calculation is performed, and all imagery used in the measurements is available for inspection and further use. Next slide, please. So in summary, then, our salamander system is a data-driven approach. So it avoids subjective measures. It utilizes large-scale existing data sets, so there's no need to visit every location to obtain the data. And it's an automated system with minimal human input. The system has requirements, though, to run accurately. It requires accurate positional data of billboard locations, and it requires sufficient imagery around each billboard. We also need the necessary computational resources to apply the algorithms. Next slide, please. So at this point, we'll open the floor to questions on the salamander system. Thank you.
Thanks, y'all. I'll start with a question. You mentioned the imagery that you use on the side of the road you get from things like Google image maps and dashboard cams. How do you guys kind of aggregate that imagery? Do you have a team that kind of just scours Google Maps to get those images? Do you have like an outreach program where people can upload their own dashboard cams, or do you have a team that goes out and drives around with the dashboard cam?
So I guess there's two ways we can do it. We can use the existing service. So Google Street View is obviously a commercial service, which has lots of imagery already collated. It's collected by Google. That imagery consists of, Street View imagery from lots of locations. So we have a database that contains the coordinates of each billboard. And using that, we make use of the Google APIs. We can request imagery from the location around the billboard. We compute some information relating to headings and distances. And using that, we extract the image sequences from a billboard. So that's one way to do it. Mapillary is another data set, works very much like Google Street View. The difference is that it's open source, that data is there, it's freely available. It's not a commercial service. So yeah, that's one way that we can obtain our information. The second way, of course, is that you go and gather your own information, and you can select the billboard that you're interested in. You fit a dash cam to your car, to your bicycle. You can even carry them around, and you walk around where humans would normally walk past the billboard. You capture all this information. So the information we need is the billboard latitude and longitude, and the imagery that surrounds that. We need the latitude and longitude as well as the images themselves.
Nice.
Heard you mention potentially walking past. So does this include the potential for pedestrian, like street furniture and/or indoor?
Yeah, absolutely. The technique itself, it just relies on locational information. That doesn't need to be that long. It really just needs to be distance and angles from the billboard to where the imagery was obtained. We have done some experiments with this from other study areas. For example, I think one of our early study areas was based in somewhere in Amsterdam, where it was in a pedestrian zone. So a lot of the imagery there was captured from bicycle and from handheld omnidirectional cameras as well. So yeah, the technique works in all those locations.
Any other questions for the group? Geopath, maybe?
I just have a quick question. Does it factor in the creative at all, and whether or not the creative is like visible from the distance, or would it be rather used to maybe inform the kind of creative that would be used on a particular billboard?
Yeah, so I guess this is something we're not doing at this point in time. So we're not interested, for us anyway, we're not interested in the content within the billboard itself at this point in time. We're solely interested in the billboard, its position within the environment and where it can be viewed from. In terms of future work, absolutely. This is something that we've spoken a lot with Hussein about, and something we're really interested in doing. In terms of the creatives, we're really interested in doing things like Data augmentation. So we've spoken a lot about actually augmenting some of the images, putting different creatives in. Using this information, then you can also use some computer vision techniques around saliency to measure how likely, I guess, someone would be to notice the billboard with the surrounding information in that environment. So yeah, it's not something we're doing, but we're definitely looking to explore that in the future.
I have a quick question.
Yeah.
I know there are certain things you can't change, like distance and how many roads have visibility to it. But if there are things that are obscuring the billboard that an owner could improve, does that kind of information filter back? So if your score is not high because of that, are there things that somebody could do to fix that?
So
it could.
Yeah.
We could, I guess, if with a low visibility index, then with it, by inspection, if you view the images and you realize that the visibility index is low because it's obscured by a tree or a hedge, then that is something that the owner could change in the environment to make it better. You may just find this being obscured by, at that particular instance in time, by traffic, and that's a one-off occurrence of a low visibility index. So inspection would certainly help to identify those cases.
Yeah, because the system's completely automated in the way that it extracts the billboard from the image. This means if, for example, a billboard is obscured, partially say obscured by a tree, then when we extract what we call a bounding box, so this is the visible area of the billboard, you only actually get that partial piece of the billboard that's visible extracted, and that's built into our measure. So instead of having 100% of the billboard visible, only 50% comes into that measure. So yeah, I think you could look at manual inspection. Like I said, each image is available, it's used in the calculation. So if someone looks and says, why is my billboard only 100, this one beside it, they can go in, they can look at each images and they can see why that's the case. All the data is there in terms of the measurements that are used to come up with the calculation. All the images that are used are there, the bounding boxes that are calculated, everything's there to be fully transparent in how we're computing these numbers.
Okay, thank you.
Dylan, did you want to get in here before we?
Yeah, I think this is some pretty interesting stuff. There's a lot of interesting work being done right now around visibility and attention. There's other groups that have approached us as well as Neuron and Salamander to try to figure out how GeoPath can help incorporate some of these things, if there's room for improvement on sort of our auditing procedures. I think it's all really interesting stuff. And I can't remember who asked the question about swapping out creative, but I think that that's something that there's a lot of room in this space beyond just a base audience impression, getting into attention and engagement. And I think there's a lot of potential around here.
Thank you.
But Hussein and I have connected a couple times to try to figure out how to potentially work with one another. I think scalability and availability of data to feed into it is something that we're certainly, one of the things that we're always wanting to make sure that this is doable everywhere. But it's interesting stuff.
Yeah, attention is getting a lot of attention. Again, it seems. I was approached the other day there's an attention council in the UK, an old friend of mine is running from Kantar Media Research. So it's like, this is, I remember when I worked at IAG when we did branded entertainment research, the measure was first called show attentiveness for television, and then engagement became the hot term of the day. So they quickly rebranded attentiveness into engagement.
I've been putting as much pressure as I can on the ARF to update their media model to help sort of provide a little bit more clarity on all those things that go beyond just exposure or opportunity to see, to a noting, to then attention and impact and everything. So there's lots of different metrics out there. So yeah, it'll be fun.
Any other questions? For
Yeah,
everyone
one
here?
more question.
Yeah, please.
So let's say I said I need these 5 boards measured. What's kind of the time to get an index?
So the computation time is it's minimal. I mean, you know, we're talking, I guess, seconds in terms of once if the imagery is available, the network's already trained. You know, it takes, you know, we probably can, the process that we call it inference when we place an unannotated image into a pre-trained network, and from that we extract the bounding box. And you know, basically it's limited by computational resources, but we can easily do, you know, hundreds every second on a pre-trained network. In terms of the network that we've seen here, I guess it's probably also important to note that, you know, this network that we're using here has been trained on a very small number of images to extract billboards. That actually the network, we used images that we manually annotated from somewhere in Australia. It was around 1,500 images in total, so 1,500 images that we manually draw a bounding box around, and we use that to train up our deep network. And those images came from Australia, and then we moved our study area to Arlington, and we just took images that were unannotated and we put them into the same network. This was a sort of academic exercise to see how robust the network was. And you know, it was amazing that it worked perfectly on these images from a totally different part of the world, considering we only used a very small example. So yeah, you know, if we have lots of more annotated images, we can really improve the system a lot better, but it's working fantastic as it is. And the inference time is really, really short. Computing the metric itself, again, you know, it's really, really fast. We're just looking at doing some what we call floating point computations. So they're just decimal numbers in terms of distances, angles. We apply a few functions there in terms of visual acuity and visible area. And yeah, we can do this like super fast. And someone mentioned about the scalability. Really, what we're limited by here is data. You know, if you have data of billboards all around the world and you have accurate positional information and visual information, there's really no limitation here in terms of this technique. You can scale it up using cloud resources. It's pretty easy to do.
On the numbers themselves, if you don't mind, what is like, so we saw 19 and we saw 401. So
Yeah.
what is like 100 represent? Is that the average visibility, and then 400 would be, how does that work?
So the numbers here, they're sort of notional. They don't really mean like 100's not perfect, or you know, 500's not perfect. It's just a notional measure, I guess. For us at this point in time, we were really interested in looking at, you know, the 5 billboards and ranking in them, you know, using that number to effectively rank them 1 to 5 in terms of visibility. I guess if you do it out on a really large scale, then you can look at maximum values and you can normalize that into whatever range that you want. But the key factors in terms of those numbers relate to visible area of billboard and distances. That's the key factors, along with the functions that normalize it based on human visual metrics.
So in the case of that one unit that had the access road right next to the unit, that's taking in, you're averaging all of the images within the contact zone of the unit, and that's how you're arriving at the score.
Yeah, there's an averaging process there. That's why it's not limited by the number of images around each billboard. It doesn't matter for 5 or 500. So we do have one averaging happen there, but as well as that, it's the visible size within those contact zones. Generally, the one with 401, it's clear to see that the billboard was much larger, and there was many more locations around that where the angle was, the billboard was more, what's the word, I guess, parallel to the road, or
perpendicular.
Yeah.
Perpendicular, yeah.